And we saved the best for last, Hiroki Moriwake, a veteran of this meeting. He'll be talking about the possibility of designing dielectric materials by Softmode engineering.
Which port can I use my...
Oh. This one here. After 15 minutes, I'll give you a sign.
Yeah.
You have 5 more after that.
Well, which one? Hmm? This one?
Ron, which one of these is it? Is it this one?
What are you asking?
He's asking about the clicker.
Whichever one's plugged in.
Oh, it's not clear. I think it's this one.
This one?
Give it a try.
Okay. So thank you for kind introduction. My name is Hiroki Moriwake from Japan Fine Ceramic Center. Today I will talk about a little bit possibility of designing dielectric material by Softmode engineering. So Softmode engineering is very simple concept for us. As shown here, the potential surface, if we have a single well, this is a para-electric. Then ion move very small this position. And if we make it soft mode, we have a double well here. It becomes para-electric to the ferroelectric phase transition. Then ion move this small well. And between these two phases, we have a very huge permittivity, as shown here. This phase has a very small energy barrier in between two variants. So ion move very large space here. So it shows the very large permittivity and polarization fluctuation as shown here. So now materials informatics is very, very popular among scientists and engineering for material scientists. The definition comes from Wikipedia, as shown here. Materials informatics is field of study that appear the principle of informatics to material science and engineering to better understanding the use, selection, and development and discovery of material. And the goal of this informatics is to greatly reduce the time and risk required to develop, produce, and develop a new material, which generally takes a very long time, for example, 20 years. So, for example, in case of lithium-ion battery material, we can calculate most of all these important property for the lithium-ion battery, the voltage and capacity and stability and conduction. So almost 10 years ago, Professor Seda in MIT at that moment doing this kind of material informatics material survey. So he calculated many of materials, something like this, then choose very good lithium-ion battery materials. And now they produce this database. This database has a calculation result for the not only the battery material, but also the all of materials. It is very, very useful tool for for us. For example, if we need battery materials, we can choose couple of elements and voltage as shown here. Then we can obtain these candidate materials as shown here. Very, very useful tool. And now I'm heavily involved in the Japanese materials informatics project called MI2I project, in Japanese material informatics project. But during this project, I found very difficult things for the material informatics to apply the realistic material investigation. The most biggest problem should be no reliable material database regarding quantity and quality and accuracy or something like that. That's the reason for this mainly experimental data is taken by the polycrystalline sample and sample preparation condition is different. And the maybe most biggest problem is corporate secrets. So they don't willing to share their very important material data. So in this case, this is one solution key to material informatics for my understanding. Focusing on bulk property. So to exclude effects of influence from the surface and grain boundary or domain or something like that, then we can, in this case, we can calculate material property using first principle calculations. So one of the example is as shown here. We're doing material informatics for the high dielectric constant material for the paraelectric in paraelectric phase, not ferroelectric. So we collaborate with a private company. Then company person submitted the patent and these literature. So nowadays, multi-ceramic capacitor desire to use very high temperature. But MLCC materials mainly composed from ferroelectric barium titanate. This temperature region is barium titanate goes to the paraelectric phase. This shows a very small direct constant. So we cannot use this high temperature region. So paraelectric and high direct constant materials are desired. Then we construct this kind of material informatics process. We can choose candidate materials from materials project database using these criterions. It's something like oxide and it is insulator and it's easy to synthesize, something like this. Then we can calculate DFPT method for the direct constant. Then choose, search for the high direct constant material. One of result as shown here. This is only for the materials number. We cannot name names, but some material has very, very high direct constant over exceeding 100 direct constant. And we choose these materials. This has not only reported high direct constant material, but also unreported materials are included. Then we choose some of these candidate material for the synthesized experiment. These synthesized experiments are carried by a private company, so we cannot know the detail of these results. One of results as shown here. This material they can synthesize in this desired crystal structure as shown here. But we looked here, it's very, very dark, maybe some vacancy or something like that. It's very leaky material. So if we want to measure this direct constant, we need much more good high quality samples. But so it's carried by the private company, so we cannot know the detail of this experiment. So, so we need some good method to develop the dielectric materials. So one of solution should be this soft mode engineering, as explained before. So now, the one of example for the we calculate for the one of example we choose this rock salt structure because it is very, very simple structure and only constructed by the MO6 octahedron. So it's very simple, so easy to understand. The methodology as shown here, we are using the PAW method implemented in the BASP code and the Phonon calculation calculated by the Phonon Pi code. The permittivity calculated DUFPT calculation. Then if we have a soft mode, we also plan to doing comprehensive soft mode analysis to determine the ground state structure. So calculation was done by this alkaline earth metal oxide, namely magnesium, calcium, strontium, barium oxide. Then to tune soft mode, we apply the pressure of this this range. And calculated this range, no soft mode were found until structure broken. It's very, very, not so excited. So it's very difficult to see, but it is calculated result for the phonon dispersion curve for the MGO at zero pressure. Polar mode as shown here, very difficult to see, but applying negative pressure, this polar mode goes down. So we can tune using applying pressure. We can tune the soft mode. This is the calculation result. If we applying negative pressure, phonon frequency goes down beautifully, and lattice parameter goes up. About 10% lattice expansion were found. And at the same time, dielectric constant permittivity goes up, as shown like here. The only ionic part show this divergence. Electric part doesn't change much. So permittivity rapidly increased the polar phonon mode softening. But this permittivity divergence were found very vicinity of structure breakdown. That this calculation show that this negative pressure structure are broken. apart from these area, permittivity increase at most 2 to 3 times, so not so significant. By changing cation, behavior doesn't change much. But critical pressure should be changed. Here, about minus 35, 30, minus 15, and for the barium oxide, very low negative pressure are needed. So phonon frequency, pressure dependence of the phonon frequency is varied by the type of cation, as shown here. And the critical pressure will correspond to ionic radius of cation, each cations. And this is a Boron effective charge change, but Boron effective charge doesn't change much, about 0.1 to 0.2 changes. So no significant change in the Boron effective charge. This means the ionic bonding nature of these alkaline earth metals. So let me summarize my talk. To discuss possibility of soft mode engineering using rock salt structure. Under negative pressure, polar phonon softening, then permittivity increased dramatically. The huge permittivity are observed in vicinity of structure breakdown pressure. Remaining question should be here. Why no soft mode, no ferroelectric phase transition in rock solid structure? It's simply because I think ionic bonding nature of these alkaline earth oxide. So for ferroelectric phase transition, covalent bonding are essential. So materials informatics and soft mode engineering, as explained here, is it successful to design the dielectric material or not? I think it is successful, but if not, maybe I will be punished by this young lady, something like this. Thank you for listening.
I have a question about your breakdown. That is, you enter the coordinates in the rock salt structure, and then you compute with a very large lattice constant, my understanding.
Yeah.
And then what does it mean, breaks down? They dimerizes or what? I imagine you can do very, very large. And so what do you mean by breakdown? How do the calculation breakdown comes out?
Yeah, no bonding, maybe. I mean that.
But I don't see. You have a cell with 2 atoms per cell. You compute the computer. You can compute with the lattice constant 1 meter. You get the result.
No. Here, here. Only 10% expand.
Yeah, but
This is broad breakdown ratio as shown here.
then I have another observation. You say covalence. We know since a long time that in order to have Born effective charge, the ferroelectricity is associated with very large Born effective charges of the 6, 7, 8, 9. And this only occurs because of covalency. Because if you don't have covalency, if you can interpret it in terms of one-year function, the one-year function sit on the nucleus, and so you have a trivial Born effective charge. You don't have any ferroelectric transition. So that seems to me really a new message. That one. Mm-hmm. Okay.
Yeah, actually, this was pointed out some years ago. There's a PhysRev letter by Eric Bosquet, Nicola Spalding, and Philip Gauzet on the alkaline earth oxides, showing that when you expand them, they become ferroelectric. So this is...
Also, if we have a cation have a covalent bonding nature.
Yeah, but it's the same as what you're showing, I think. Anyway, I sent you the paper, so you'll see it.
Well, I have two things. I mean, one is that the statement that sodium chloride structures are not polar, at least, is totally wrong. I mean, all the phase change material are polar, and so I mean, it's a sodium chloride structure for the reasons we just heard are in fact polar, and some of them are probably even switchable. I mean, we had talks here in the meeting which talk about this one. But I don't want to prolong this. Can I say something to the organizer? Sure. I think we should thank the organizers for this wonderful meeting, because it was really well organized and many people are still here. I mean, the majority is still here. And I think it was wonderful, including the dinner yesterday. And so Ron and Peter and everybody, I think we should give them a round of applause.